When you think of medicine, what's the first thing that comes to mind? It's probably a pill, right? I mean, it's been the standard for decades. But what if we could totally transform that simple dose into an intelligent system, something that works precisely where and when your body needs it? Well, that's the incredible promise of strategic biomaterials, and we're about to dive deep. So let's just start with this fundamental question. Is a pill really always the best medicine? For so long, it was just the default, the only way we did things. But, as our understanding of biology gets more and more sophisticated, our delivery methods have got to catch up. And this chart, wow, it just lays out the whole problem perfectly. With conventional dosing, like a pill you take every few hours, your drug levels go on this wild roller coaster. They spike up, sometimes into a toxic range, and then they crash, often falling below the level where they're even doing any good. This whole peaks and valleys thing is just inefficient, and it can cause all sorts of side effects. The goal, what we're aiming for, is that steady, controlled release line, keeping the drug right in that sweet spot, the therapeutic window. Okay, so here's our game plan to really get our heads around all this. First, we'll break down the drug delivery problem. Then, we'll look at the controlled release solution. We'll get into the nitty-gritty of how the basic mechanisms work. Then comes the really cool stuff, smart biomaterials. And finally, we'll take a look at the real-world challenges and what the future holds. All right, first up, the drug delivery problem. Or, to put it another way, why a simple pill just doesn't cut it anymore. We've already touched on this, but let's really nail it down because it is the single most important concept here, the therapeutic window. Seriously, think of it like a target for an archer. If you shoot too high, the drug becomes toxic. If you shoot too low, it's totally useless. The entire goal of modern drug delivery is to hit the bullseye and just stay there. The old way of doing things faces a ton of hurdles. A lot of drugs have what's called low bioavailability, which just means a tiny fraction of the pill you swallow actually makes it into your system. Your stomach has a harsh place. It can just chew up the medicine before it does any good. And on top of that, absorption rates can be all over the place. And, like we saw, those peaks risk toxicity, while the valleys mean the drug just isn't working. It all leads to needing frequent doses, which, let's be honest, is super easy to forget. Which, of course, brings us to a much better way of doing things, the controlled release solution. So how do we actually get that steady, perfect control? Well, the key, the real game changer here, is biomaterials. And look, these aren't just bits of plastic. These are incredibly sophisticated, specially engineered polymers and lipids that act like microscopic cargo ships, designed from the ground up to release their therapeutic payload slowly and steadily over long periods. The goals here are pretty straightforward, but man, they are revolutionary. First, maintain those steady drug levels. No more roller coasters. Second, you can reduce how often a patient needs their medicine, which makes it so much easier to stick with the treatment. Third, and this is huge, we can actually target specific locations in the body, which can dramatically cut down on side effects. And finally, these materials act like a shield, protecting the drug on its journey through the body so it arrives safe and sound. Okay, so how does this stuff actually work? Let's get into the basic mechanisms, the real foundation of all this control. Now, this is super interesting because it breaks down the two main ways this is done. On one side, you've got reservoir systems. A great way to think about this is a tiny little capsule with the drug locked inside, and it slowly leaks out through a special membrane. The classic example? A nicotine patch. Then, on the other side, you have matrix systems. Here, the drug is mixed all the way through a polymer, kind of like chocolate chips in a cookie. The drug gets released as it diffuses out, or as the cookie itself slowly and safely dissolves. That's the principle behind some amazing biodegradable implants for cancer treatment. Now, don't get me wrong, these systems are a massive leap forward. They give us that steady, predictable release, and they make life so much easier for patients. But they're not perfect. They do have some limitations. For one, the release rate isn't always perfectly constant. It can sometimes slow down as the drug starts to run out. And if the polymer material breaks down in an unexpected way, well, that can mess with the whole process. But this is where things get straight out of science fiction. Enter smart biomaterials. We are now talking about medicine that actually, literally responds to you. So what in the world is a bioresponsive material? Think of it like this. It's a specially engineered package that holds its drug cargo on total lockdown.
it doesn't release anything until it gets a very specific signal, a trigger, either from inside the body or even from a doctor on the outside. This isn't just a slow leak anymore. This is a true on-demand system.
And this quote right here, it just perfectly sums up the dream, the holy grail of this entire field. See, the ultimate goal isn't just releasing a drug slowly. It's about controlling the what, the where, and the when of a treatment with absolute pinpoint precision, targeting only the cells that need it and leaving everything else alone. So what are these triggers? Well, let's look at a few. First up, pH. This is so clever. It turns out that many tumors create a slightly more acidic environment right around themselves. So scientists have designed biomaterials that are totally stable at normal body pH, but the second they enter that acidic tumor zone, they fall apart and release their drug payload right where it's needed most. Okay, another powerful trigger? It's called redox. This one uses the unique chemistry inside our cells. The chemical environment inside a cell is completely different from the bloodstream outside. So by engineering materials that are sensitive to this change, we can create drug carriers that stay sealed tight in the blood, but pop open to release their cargo only after they've been swallowed by a target cell. It's incredible.
And get this, the triggers don't even have to be biological. We can use forces from outside the body. I mean, just imagine loading a drug into tiny magnetic nanoparticles. A doctor could then use an MRI machine to activate those particles and release the drug at a super specific spot. Or they could use focused ultrasound waves to literally pop tiny drug-filled bubbles right where they're needed. It gives doctors real-time, hands-on control over treatment.
Okay, this all sounds absolutely amazing, right? But what's the holdup? What's it going to take to get this stuff from a lab bench into your local hospital? Let's talk about the challenges and the future. So the single biggest hurdle, the main boss battle, if you will, is something called the foreign body response. Your immune system is just ridiculously good at its job, and its job is to identify and attack anything that isn't you. So when you implant a biomaterial, the body can see it as a foreign invader and try to wall it off or destroy it, which can completely stop the device from working. Overcoming this response is a massive, massive area of research. But here's the thing. Despite that huge challenge, the progress has been absolutely spectacular. This isn't just a sci-fi dream. The very first controlled-release polymer systems were developed way back in the 60s. By 1995, we had the Gliadel wafer, an FDA-approved biodegradable implant that delivers chemotherapy directly to brain tumors. And just a few years ago, in 2018, a therapy called patisiran was approved, a groundbreaking RNA treatment that's only possible because of its sophisticated lipid nanoparticle delivery system. The progress is real. And why does all of this matter so much? Well, the stakes are just huge. We're talking about a global pharmaceutical market that's expected to be worth, get this, $1.3 trillion. Improving how we deliver these drugs doesn't just lead to better patient outcomes, it has a massive economic impact and unlocks the potential of powerful new medicines that would otherwise be totally unusable. So we'll leave you with this final thought. We are very clearly moving from a world where medicine is something you just swallow to a future where medicine is something we strategically deploy. Imagine a smart, microscopic army sent on a precise mission inside your own body. The potential is absolutely staggering, and we're just beginning to see it unfold.